So it's a pleasure to introduce Rishi Gurnani, who is a fourth-year doctoral candidate, doctoral student. He comes to us from the University of California, Berkeley, with an undergraduate degree in material science and engineering, and this is his fourth year, so he's about finishing up his fourth year. Let's see. Let me take this opportunity to highlight some of the impressive stuff that Rishi has done. Let's see, Rishi. So his work is right at the intersection of material science and artificial intelligence. And he has really demonstrated tremendous breadth as well as depth, as you will see. And he has also worked on many projects. And although he will highlight only one project today, I think, correct? Is that it?
Yeah.
He's worked on a couple of more, right? And he's impacted many projects as well as many people. So with that, I'm going to hand it over to Rishi. Tell us more.
Thank you, Rumpy. I think someone was trying to get in.
It's coming from the back.
Okay, well, watch out for that, please. But yeah, thank you, Rumpy, for the nice introduction. I want to start off by thanking each of you for being here, whether you're here in person or whether you're here online virtually, or whether you're here to learn more about my work or to support me, or maybe you're here for the donuts, whatever the case is. Thank you for coming. So yeah, with that, I'm here to talk about the work that I've done over the past 4 years of my PhD. Trying to summarize this body of work in just a few words was an interesting challenge, but ultimately what I thought was a suitable title is Advances in Artificial Intelligence for Accelerated Discovery of Energy Storage Polymers. I want to start us off with an anthropological perspective. Oh, my phone's going off. Second. Yeah, good. All right, I want to start us off with a bit of an anthropological perspective. A pivotal characteristic that sets humankind apart from the remaining animal kingdom is the development of tools, from cookware in the Stone Age to handheld computers in the current Silicon Age. That these eras are named after materials is no coincidence. Rather, it emphasizes a central truth. The technological progress of humankind depends on the discovery, design, and optimization of materials. For technologies of sufficient complexity, finding a suitable material can feel like searching for a needle in a haystack. One of the challenges is that oftentimes the applications we're interested in impose conflicting property requirements. One example from the polymer world is dielectrics for electrostatic capacitors. Here, the polymers need to simultaneously have a high band gap and a high dielectric constant. One way to achieve a high dielectric constant is to introduce more and more pi electrons into the polymer, since these electrons are easily polarizable. However, at the same time, these pi electrons occupy energy states that narrow the band gap, and so these two properties fight with one another. Another example is polymer membranes for gas separations. Here, polymers need to simultaneously have a high permeability and a high selectivity. We can achieve a high permeability by increasing the porosity or free volume within the polymer, and we can achieve a high selectivity by maintaining a narrow pore size distribution. However, as nature would conspire, as we increase the free volume and therefore the permeability, the pore size distribution tends to widen out, driving down selectivity. And I mentioned these two applications in particular because they're both areas that I've worked on during my PhD. But in the remainder of the presentation, I'll mainly focus on this application, which is capacitors. So if you open up a Toyota Prius and you sort through its guts, you'll eventually find something that looks like this. It's a capacitor bank, which is simply a device made up of several individual modules called capacitors. Capacitors are devices that are used to store energy. They're made up of two main components, electrodes, which store charge, and dielectrics, which prevent charge from passing between the electrodes. It turns out that in a capacitor, the figure of merit energy density depends on the choice of dielectric material. The current industry standard dielectric material is biaxially oriented polypropylene, or BOP. BOP is favored for a number of reasons. For one, it has a high breakdown strength, which means that it can withstand large electric fields. Second, it has a low loss, which means that only a tiny fraction of energy gets lost as heat during charging or discharge. And finally, it's cheap. However, BOP has a low dielectric constant, which, as shown by this equation at the bottom of the slide, means that it has just a moderate energy density, which could be further improved. Here we have energy density on the y-axis versus temperature on the x-axis for a handful of commercially available polymer dielectrics. And here is BOP. It starts out with a solid energy density around room temperature, but then rapidly degrades as temperature increases, and the polymer completely breaks down below 125 degrees Celsius. There are other commercial dielectrics, such as FPE, which can withstand higher temperatures. However, they all have low energy densities. Prior to my time, the Ramprasad group has developed dielectrics with improved performance up to 90 degrees Celsius. The challenge now is finding polymers that are suitable for higher temperature applications. In other words, we want to find polymer dielectrics that lie in this region. In order for a polymer dielectric to lie in this region here, we must simultaneously have several properties. First is dielectric constant. The second is high breakdown strength, or equivalently a high band gap or high electron injection barrier, which are positively correlated with high breakdown strength. These two properties here ensure that the polymer will have a high energy density. Simultaneously, we want a high glass transition temperature, or TG, so that the polymer remains functional even at extreme temperatures. Unfortunately, it's not so easy for a commercially available polymer to meet each of these criteria simultaneously. So let's focus on this center plot here, which plots TG on the y-axis versus band gap on the x-axis. What this plot shows us is that we can either get a high TG or a high band gap, but not both, which is what we really want. This plot over here tells a similar story. We can either get a high dielectric constant or a high band gap, but not both. So the objective of this work is now clear. It's laid out right in front of us on this slide. We want to find polymers lying in these gold regions so that we can store energy more efficiently in capacitors. As I mentioned, this type of material search can feel like searching for a needle in a haystack because the number of possibilities to consider is truly staggering. Let me show you what I mean. Let's consider this square here as representing the entire polymer universe. That is the entire set of polymeric materials that could be made if only we had enough time. This space can be divided into polymer composites and neat polymers. The space of neat polymers can be further subdivided into metal-containing polymers and all-organic polymers. The space of all-organic polymers is made up of homopolymers, copolymers, blends, network polymers, etc. Homopolymers can either be made from condensation or addition reactions, and addition polymers are typically either ring-opening polymers or polyvinyls. By polyvinyls, I mean things that can be made out of ethylene, propylene, styrene, etc. In particular, let's focus on polymers that look like this. That is polystyrene with 3 functional groups anywhere on the benzene ring. The number of polymers that could be made matching this description is 10 to the 14th power. In other words, this tiny sliver of the polymer universe contains 10 to the 14 polymers. Actually, the number is greater than that if you consider things like stereochemistry and mono, di, tetra, and penta substituted variants of polystyrene. For context, the number of cells in the human body is also around 10 to the 14th power. And just as we cannot go into the doctor's office and expect them to give us a detailed report of what each individual cell in our body is up to, likewise, we cannot go into the lab and make every single possible polymer and test its properties. This is where artificial intelligence can help by taking part, not all, but part of the search out of the lab and into the computer. For us, this process starts with materials data. From this data, we can train structure property models using machine learning. As the name suggests, these models take as input a structure and then output predicted properties of that structure. In parallel, we can build a huge list of structures to search through. We can input this list into our models, which will then predict the properties of each structure in the list. And we can keep those with the best predicted properties and throw away the rest. At this point, there are just a handful of structures left, a small enough number that they can be analyzed one by a human domain expert to decide which should be synthesized and characterized in the lab. This approach works well when our structure property models are fast and accurate, and when our list of structures is synthetically accessible, meaning that we can reasonably expect that a large number of structures that we've proposed can actually be made in the lab. Developing AI tools that meet these criteria is a non-trivial task and has been one central focus of my PhD. Another focus has been using the tools that I've developed to discover advanced materials, including dielectrics for capacitors. In the rest of the talk, I'll start by sharing a handful of these discovered materials, and then I'll talk about the tools that I developed to help get us there. Just to reiterate this, the next section will be on the screening, synthesis, and characterization of dielectrics. Then I'll get into methods, starting with an algorithm for structure property modeling of polymers. And then I'll talk about two methods for chemical structure generation of polymers. And this first bullet can actually be further subdivided. First, we'll talk about dielectrics for high temperature, high energy density capacitors. And then we'll also add sustainability into the mix as an additional target metric. So our screening process for polymer dielectrics started with a data set of polymer structures that I created. This database contains over 28,000 polymer structures that could be potentially be made using ring opening metathesis polymerization, or ROMP. I chose ROMP in particular because this class contains polymers with the best reported high temperature energy density to date. After the list of structures was built, then I input those into structure property models, which predict the band gap, TG, and dielectric constant of each polymer list. Then I keep those with the best predicted properties. Specifically, I look for band gap greater than 4 electron volts, TG greater than 100 degrees Celsius, and dielectric constant greater than 3. So out of all the polymers with a high predicted performance, I selected the top 12, and I sent those to our polymer chemist friends at the University of Connecticut in Dr. Satsing's group, and they selected, based on their expertise, 4 out of the 12 structures that I sent them to synthesize in the lab. And here are those 4 polymers. They're all polynorbornene imides, characterized by bicyclic rings in the backbone and a pendant benzene ring. Of course, they differ in a few respects. This position on the ring can either be an oxygen or carbon atom, and each of the 4 polymers contains different substituents at different places along the benzene ring. Each of these 4 AI-generated polymers was able to be synthesized and was then electrically and thermally characterized. And here is the result of that characterization. We have our experimental measurements in plain text and our ML predictions in parentheses. And overall, we see that these measurements and predictions agree quite well. The average error for the band gap prediction was around 0.4 eV, 12 degrees Celsius for TG, and 0.7 for dielectric constant. And the measurements that I shared on the last slide were obtained by the Satsing and Tsao groups at the University of Connecticut. So how do these measurements stack up against commercial dielectrics? Well, each of the 4 polymers lies in the desired TG band gap quadrant, and 3 out of the 4 polymers lie in the desired dielectric constant band gap quadrant, with this polymer named PONB2Me5Cl standing out in particular. Because of its unique combination of properties, high TG, high band gap, high dielectric constant, this polymer also possesses an unprecedented energy density. At room temperature, the polymer's energy density is double that of BOP. More important, though, is what happens at higher temperatures. At 200 degrees Celsius, the polymer's energy density is 11 times greater than the best commercial alternative at this temperature, half-ton. So what does this high energy density get us? I want to remind everyone that energy density is simply equal to the total amount of energy stored in the capacitor normalized by its volume. So the high energy density allows us to open up opportunities for lightweighting. For example, we can reduce the size of the capacitor bank up to an order of magnitude while keeping the total amount of stored energy constant. Or we can increase the total amount of stored energy up to an order of magnitude while keeping the size of the capacitor bank constant. Oh. Okay, 1 second. Cool. All right. So yeah, so I talked about the lightweighting aspects. We can either increase the energy density, the total amount of energy and keep the capacitor bank the same size, or we can reduce the size of the capacitor bank and keep the total amount of energy stored constant. The other benefit is that because of the thermal stability of this polymer, there's no need for external cooling devices. So long, of course, as the temperature of the capacitor bank does not exceed 200 degrees Celsius, which is a reasonable expectation for a number of applications, including hybrid electric and rail vehicles, pulsed power systems, and wind pitch control. Through the discovery of this polymer, my work, and really the work of the whole team, has expanded the use cases of capacitors within the 125 to 200 degrees Celsius range, at which there is currently no good commercial solution. Right. To this point, I've placed great emphasis on high temperature energy density. Now I want to add sustainability to the discussion. Sustainability is a multidimensional word, which can mean many different things in different contexts, but one aspect relevant to this work is choice of solvent. Each of the polymers studied in this work was made using solution polymerization. That is, we take our monomer, we dissolve it in some solvent, and then the solvent acts as a reaction medium in which the polymerization can unfold in response to some stimulus. Polymers all across the world are made using this method, which means that huge amounts of solvent are produced each year. Some of the polymers that we currently rely on use solvents that are harmful for us and for the environment. And unfortunately, our polymer PONB2Me5Cl is no exception to this rule. To drive home the point about how potentially dangerous these solvents can be, I want to share the example of carbon tetrachloride. Up until 1989, it was used as a solvent, but then we banned it because we realized it was poking a hole in the ozone layer. Today, we still use hydrocarbon solvents, which are mainly derived from petroleum, and that's bad for obvious reasons. Ideally, we would like to use green solvents, like water, which is renewable, and it's not toxic to humans or to the environment. Another good option is ethanol, because it can be derived from biomass like corn husks. In addition, we know that production of ethanol on an industrial scale is reasonable, since up to 10% of the gasoline in your car is ethanol. And in addition, we know that at least in moderate doses, ethanol is not toxic to humans, since we've been using it for centuries to have a good time. But all this to say, our next goal is to find polymers that retain all the performance attributes of PONB2Me5Cl while also being soluble in water or ethanol. Previously, I was focused on polymers that could be made using ring opening metathesis polymerization. However, these polymers tend to have a poor solubility profile. So instead, I shifted my focus to polyimides for two reasons. One, there are examples of polyimides that are currently being used as high temperature dielectrics. And two, there are examples of polyimides, or at least their polyimic acid precursors, which are soluble in water and or ethanol. So our screening process for polyimide dielectrics followed a similar workflow to what we used before for RUMP. In this case, though, we have a database of 66,000 polyimide structures. We fed those into our structure property models, including one model which can predict polymer solubility. Out of the 66,000 polyimides, I've plotted here roughly 1,800 of them. Each is predicted to have a TG greater than 200 degrees Celsius, a band gap greater than 4 electron volts, and a dielectric constant greater than 3. Roughly half of the 1,800 structures here are predicted to not be soluble in water or ethanol, and those are represented by the gray pluses. The other half is predicted to be soluble and therefore is represented by these green dots. I want to draw your attention to these 4 polymers in particular, because the monomers corresponding to these polymers can either be purchased directly for relatively cheap, or the monomers, we believe, can be synthesized in 1 or 2 steps. So I'm working with Pratish Akluchkar and Dr. Satsing's group to see if we can turn any of these polymers into a reality. So just to briefly recap the past 10 slides or so, the main achievements so far are that we have discovered a handful of polymers with an attractive combination of TG, band gap, and dielectric constant. One of these polymers has an unprecedented energy density, which is 11 times the best commercial alternative at 200 degrees Celsius. And we have taken some initial steps toward finding similarly productive polymers that are also environmentally friendly. Taking a step back, one of the main factors that has made this project successful is that we had effective AI tools at our disposal. We had fast and accurate structured property models, and we had an AI system capable of generating polymers that could be synthesized in the lab. These methods were developed in the course of my dissertation, and in the remainder of the talk, I'll talk about how they work, starting with structured property modeling. The starting point of any ML model is data. For structured property models, the data looks something like this. We have one column listing the structure or material, and another column listing the properties corresponding to that structure. The next 2 steps are fingerprinting and learning. In the fingerprinting step, we take the raw text, maybe our structure's name, and we convert that into a machine-readable numerical vector. This vector is called a fingerprint because it uniquely describes the structure. In the learning step, we learn whatever relationships exist between the fingerprint and the properties of interest. This set of relationships is the structure property model, represented by F hat here. And once we have it, we can predict the properties of unknown structures. As you might have guessed, one of the key steps in this whole workflow is the fingerprinting step. A successful approach to fingerprinting polymers has previously been developed in the Ramprasad group as part of the Polymer Genome Project. The key feature of this approach is hierarchy. That is, each of the individual descriptors in the fingerprint, also called features, are organized across physical length scales. At the smallest level, we track the presence of small substructures within the polymer. So a given descriptor is given a value of 1 if the substructure is in the polymer and a value of 0 if not. Moving up a rung, we check for the presence of larger substructures now. 1 if the substructure is there, 0 if it's not. And finally, at the highest level, we move beyond these binary features and compute things like what's the length of the largest side chain in the polymer, what's the shortest distance between rings in the polymer, etc. This approach works well because it focuses artificial intelligence on chemical features that are supported by decades of science and natural intelligence. For example, we know that things like side chain length impact several properties, including TG. While this synergy between artificial and natural intelligence is appealing, there are some downsides. For example, it can take a long time to compute things like side chain length. To speed up the process, I have developed a fingerprinting approach for polymers based on the graph neural network. Here, instead of computing expensive features, we restrict ourselves to cheap features. The starting point is a polymer repeat unit, polyethylene glycol in this example. We then feed the repeat unit into what I call the encoder, which has 3 tasks. First, the encoder converts the repeat unit into a mathematical graph with atoms as nodes and bonds as edges. In the second step, an edge or bond is added across the periodic boundary. And we do this to achieve invariance to translation. For example, this repeat unit and this repeat unit are equivalent, and so their graphs should also be equivalent. So if we don't have this periodic edge here, then in this repeat unit, the oxygen will only be bonded to 1 carbon, whereas here it's bonded to 2 carbons, right? So the graphs won't be equal. So if we add the edge, we can just resolve this issue. In the third step, we compute a fingerprint for each atom and each bond in the graph. And we compute things like element type, so is the atom oxygen, carbon, etc., and bond type, is it a single, double, triple bond, etc. And again, these features are cheap to compute relative to things like side chain length. Now, after the encoder has done its thing, we feed the graph into a neural network. The neural network learns the local atomic environment around each atom, and then it uses this information to spit out a fingerprint for each atom in the graph. So the output of the neural net in this example would be a 3 by D matrix, where D is the dimension of each atomic fingerprint, and 3 is there because there's 3 atoms in this repeat unit. After we have the atomic fingerprints, we kind of compress everything into one fingerprint representing the entire polymer just by taking the mean. And we take the mean to achieve invariance to linear transformations. So this repeat unit and this one are each equivalent, and so their fingerprints should also be equivalent. If instead of taking the mean, we did something like taking the sum, then this fingerprint would be smaller than this fingerprint, simply because it has fewer atoms. But if we take the mean, then we can just resolve this. All right, so at a high level, at least, we understand how the graph neural network works. So what? Well, I wanted to time how long it took to fingerprint a set of 13,000 polymers, and the comparison is between the graph neural net approach and the polymer genome approach. And here are the results. It took the polymer genome approach around 1,700 seconds to fingerprint the set of polymers, and it took the GraphNet around 30 seconds to perform the same task, which corresponds to a speed up of 56 times, and we're happy with that result. Of course, speed is only one important component of a fingerprint. Another important component is accuracy. In other words, if I take a structure property model and as input I feed it the graph neural net fingerprint, does the accuracy of that structure property model increase or decrease? To answer that question, I compared the polymer genome approach and the GraphNet approach head to head on over 30 different properties. And here are those properties. They span a number of different classes. So we have thermal properties, electronic properties, mechanical properties, gas permeabilities, and more. And what we find is that for 30 out of the 34 properties, the GraphNet approach is either comparably or performs better in terms of accuracy. And again, we're happy with that. So due to these two benefits, speed and accuracy, I opted to use the graph neural net approach when screening the set of 28,000 ROMP polymers and 66,000 polyimides, which, as you now know, resulted in the discovery of PONB2Me5Cl. So this concludes the discussion on structure property modeling. And now I'll talk about two methods that I developed for chemical structure generation. Broadly, data-driven approaches to polymer design fall into one of two categories. They either solve the forward problem or they solve the inverse problem. In the forward problem, we create a big list of polymers, and then for each polymer in the list, we predict its properties. Then at the end, we can comb through the list and see if any one has predicted properties meeting our desired targets. And this works in a lot of cases, but in other cases, if there are no polymers in your list meeting your targets, then, kind of out of luck. But there's another option. We can reverse the direction. and solve the inverse problem. Here, we start with our targets. We input those into a model, perhaps a machine learning model, and then we have the model generate polymers that are predicted to meet our targets. And in principle, we can continually sample our model until it gives us a polymer that we're happy with. Traditionally, solutions to the inverse problem have been seen as something of a holy grail. In this work, I've developed an algorithm called polymer graph-to-graph translation, or poly-G2G, which solves the inverse problem for polymers. The underlying idea here is that an attractive method of designing new polymers is to chemically tweak known polymers. A canonical example from literature is the case of polyethylene and polyacetylene. Polyethylene has a relatively low TG of around 195 Kelvin. However, if we replace just one single bond per repeat unit with a double bond, we get a massive increase in TG of around 130 Kelvin. So the idea here is that if we can train poly-G2G to learn from these examples in literature, then we can harness that knowledge to create new polymers from known polymers, as in this example here. We can aim poly-G2G toward a number of different design problems, but in the paper that I wrote to demonstrate the algorithm, the goal was to find a polymer with a high band gap, a high electron injection barrier, and a high TG. Depending on the use case, you can change the properties that you're interested in, or change the number of properties as well. But in any case, the starting point is a seed data set of 13,000 polymers. From this data set, we create pairs of chemically similar polymers. One member of the pair is high performing, meaning that it has a high value for all of our properties of interest. And the other member of the pair is low performing, meaning that it has a low value for at least one of the three properties of interest. These polymer pairs serve as training data, teaching poly-G2G how to convert a low-performing polymer into a chemically similar high-performing polymer. Once we have our model, we can sample low-performing polymers from our data set, input those into our trained model, which then outputs novel and hopefully high-performing polymers. Now that we understand how poly-G2G works at a high level, let's take a look under the hood. We start, as I mentioned, with a low-performing known polymer. From this, we create what I call a pseudopolymer, which is simply a dimer terminated by hydrogen atoms. Then we map the pseudopolymer into both a junction tree and a graph. These data structures are basically the same, except for one key difference. In the junction tree, each ring atom is collapsed to the same node, whereas in the graph, each ring atom has its own node. Then I map both the junction tree and the graph into embeddings, which are simply vector representations of the polymer in a learned numerical space. Then I concatenate the embeddings, and I feed them into an ML model called the VJTNN, which then outputs a distribution of chemical translations. I sample a translation from this distribution, and I add it to our concatenated embedding, forming a translated embedding. Then I decode this translated embedding into a junction tree. And as you'll notice, this junction tree is very similar to the one we started with, except for the addition of this nitrogen node. And the addition of this node is a direct consequence of the translation that we sampled from the distribution. Next, I decode the junction tree into a graph, and the graph into its corresponding pseudopolymer. And again, I've circled the result of the translation. And finally, we map the pseudopolymer into several polymers by replacing pairs of hydrogen atoms with periodic boundaries. And I should mention that our implementation of the VJTNN borrows from the work of Jin and coworkers. So in this work, I use poly-G2G to generate around 800,000 polymers, 93% of which are chemically valid. This is actually a substantial improvement over previous approaches in which around 27% of the generated polymers were chemically valid. I then narrowed this huge list of polymers down to 20 using a fitness function. And for each of these 20 polymers, we performed DFT and MD calculations to calculate the electron injection barrier, band gap, and TG of each polymer. Out of these 20, 10 polymers had computed properties matching our objectives. And here are those 10 polymers. On the left, we can see that the DFT computed electronic properties exceed the targets for each polymer. And likewise, the MD computed TG exceeds the target. What these results tell us is that quantum mechanics and Newtonian mechanics, the basis of DFT and MD respectively, validate poly-G2G's ability to design high-value targets. Out of the 20 polymers that we studied, poly-G2G was correct on 10 of them, and we were happy with that result. And I want to thank Dr. Deepak Kamal, Shivang Shukla, there, Dr. Hari Sahu, and Dr. Huan Tran for conducting the DFT and MD calculations. So now a natural next question is, okay, can we make any of these polymers? To me, at first blush, they look relatively benign. The main chains aren't too long or complex, neither are the side chains. However, we should remember that at no point during the training process was poly-G2G made aware of polymer chemistry. Therefore, it's not able to generate synthesis pathways for the polymers that it proposes. This led us to think about a second method for chemical structure generation of polymers. Here, the goal is to develop an AI system that takes in a set of molecules and then goes through a set of chemical rules to propose a set of polymers that could be made using those molecules. And rather than having the AI system learn these chemical rules autonomously from data, we give it the rules in advance. These rules are extracted from published literature and textbooks. After this step, we collect a database of 8 million purchasable molecules. We feed these into our AI system, which then uses its chemical rules to generate a massive set of over 233 million polymers. To understand how this system works in greater detail, let's use the example of ROMP. So, as I mentioned, the starting point is we throw 8 million molecules at our system, and then it uses rules to decide which molecules are compatible with a given reaction, ROMP in this case, and which molecules are not compatible. So the first rule that I put into the system is that for ROMP, the molecule must be a cyclic olefin. So molecules like this one that are not cyclic olefins are thrown out. The second rule is that the cyclic olefin should have enough ring strain, since that's typically the thermodynamic driving force in ring opening metathesis polymerization. I use two proxies to assess if a molecule will have enough ring strain. First, if the molecule has 6 atoms in the ring or too many atoms, it's thrown out, since these rings typically don't have enough ring strain. And second, if there are electrophiles adjacent to the cyclic olefin group, then the molecule is thrown out, since these electrophiles tend to distribute ring strain. In the end, out of the 8 million molecules, 28,000 met both of these rules, and the system creates 1 polymer per molecule. So this rule set yielded 28,000 polymers. In a similar fashion, we created sets of rules for 5 other polymer families. And in total, over the 6 families, as I mentioned, over 233 million polymers were generated, including, of course, PONB2Me5Cl. So this is the approach that we used to generate the structures that led to PONB2Me5Cl. All right, so the creation of this database was a team effort. I want to thank Dr. Deepak Kamal and Dr. Chris Kunit for laying a computational foundation that I could build upon. I also want to thank Dr. Stuti Shukla, Dr. Greg Satsing, and Dr. Rob Daniels for contributing some of the reaction rules that are used in this AI system. All right, that was a lot, but let me take a few minutes just to tie everything into a bow. So over the past several years, I've spent a lot of time working on capacitors. This work has culminated in the discovery of a polymer that maintains exceptional energy density over a broad temperature range. I've also spent a lot of time working on AI methods, including an algorithm for advanced structure property modeling polymers, and 2 methods for chemical structure generation of polymers. Despite the focus on capacitors in this presentation, I've also had the pleasure of working on other applications. For example, I've worked on polymer membranes for gas separations. Here we use AI to propose polymers that are predicted to surpass the 2008 Robeson upper bound. And I'm currently working with Dr. M.G. Finn and his group to figure out the best way to synthesize some of these polymers. Then we can actually test to see if they do surpass the 2008 Robeson upper bound, which would be a big achievement. I've also had the pleasure of working on other materials classes besides polymers. My first authored paper was actually on metal organic frameworks, or MOFs. Here, we proposed high-performance MOFs for methane storage, and this was a collaboration with Dr. David Scholl's group. I've also worked on MOFs for oxygen-helium separation, and this was another collaboration with Dr. Scholl's group and led by Shubham Jamdade, a student of Dr. Scholl's group. And here's a list of my publications. All right, going forward, there's a lot of work to be done. My work has revealed a polymer with exceptional energy density up to 200 degrees Celsius, but there's even more demanding applications that require thermal stability up to 400 degrees Celsius, like space exploration. Finding materials that meet these criteria is going to be a challenge, but multiple pathways should be explored, including the rapid expansion of the Polyverse database. This can be achieved by increasing the number of molecules that the system uses or increasing the number of rules used in the system. In addition, we should go beyond homopolymers. My work has mainly been focused on optimizing the chemistry of the homopolymer repeat unit. But as I showed you earlier, only a small patch of the polymer universe is covered by homopolymers. And so it may well be that the materials we're looking for are hidden in those other regions. Finally, I want to thank all the people who helped me over the years, including my collaborators, my mentors and peers. Thank you for your guidance. I want to thank my friends and family. Without your support, this truly would not be possible. Some of you have been supporting me for the past 4 years, some of you for my entire life. So thank you. I want to thank my committee now for their time. Dr. Jacob, Dr. Lively, and Dr. Zhang. I want to thank also Dr. Zhang, who is not only on my committee, but has also served as my co-advisor for the last couple of years. I want to give especially a massive thank you to Dr. Ramprasad. Rampi, thank you for giving me an opportunity, for believing in me and for supporting me over all the years. I count myself as lucky to be a member of the group, and I look forward to making more memories. And lastly, I want to acknowledge the sources that funded this work. So thank you, and I'm happy to take any questions.
All right. Great presentation. The floor is open for questions from the general audience. I should also note that Rishi's family is here. Thanks for joining us, and you're also welcome to ask questions. So this floor, as well as the virtual floor, is open for questions, so please go ahead. Yeah.
I have a practical and maybe naive question.
Okay.
When you discover a capacitor material that good, what can we do with it? Who can we give it to?
Yeah, it's a great question. So there's a couple applications that I mentioned. So hybrid electric and rail vehicles. So the people engaged in that space, I don't know, think of Tesla, maybe we should call them. There's wind pitch control. So, you know, in windmills, you know, you have to organize what direction the blades go. And then there's also pulse power systems. So think of defense, like your General Atomics or something like that.
How about the airline industry?
Yeah, so the temperature requirements are a bit higher. So, you know, think like 300 degrees Celsius or 400. So we're on our way. I mean, you could use something like this. You just need to put in some cooling systems. But at that point, you might want to use like BOP instead if you're going to put cooling systems in there.
For solar panels.
Potentially, I mean, I'm not aware of capacitors being used in solar panels, but I don't know, maybe they are.
Rishi, Jeff Garber's here, another sort of follow-up.
Further questions?
Hey, Roppy, Jeff Garber's here. Can I get one in real quick?
Absolutely. Please go ahead.
All right, thank you. Yeah, again, sort of on the practical side, I think from a non-practitioner that it seems like this research is leading to sort of order of magnitude increases in the rate at which polymers with certain properties can be discovered. One can only anticipate that that will accelerate as new AI technologies, new AI hardware platforms, new resources become available. So I'm kind of wondering, I mean, how do you kind of know when you're done, right? I mean, if you need a polymer that has a certain set of properties, so if I stop now and say, okay, I'm going to go into manufacturing on this one, and 3 months later, here's a new one that now has, is water soluble or has even better performance requirements or whatever. Kind of, how do you know when it's good enough, and how do you know when you should sort of wait and see if the machine's going to propose something else in a couple of weeks?
Yeah, that is a great question. It does challenge the paradigm of traditional material science. I mean, just to explain that a little bit, like the Department or Office of Naval Research, for example, part of the DoD is one of the people who funded this work. And so they have you can apply for grants at 5 different levels of technology readiness. And so this is at the most fundamental level. So, we're trying to play with the chemistry. But then you can imagine you go all the way up from 1 all the way to 5, where 5 is commercialization. And so, typically these programs will, like our basic science one, will run for 4 years. And you take whatever the best polymers you found in those 4 years, and then you apply for the second level, and you have 4 years to get those, maybe on like a couple 100 grams at a time of polymer films or whatever. And then you can keep going to the next one. Now, yeah, we have a different paradigm now. It's possible that in those 4 years, the ML algorithm will come up with something better. And it's something that we should all think about. I don't have an answer about how to address that challenge of rapid change. I think it exists in all parts of society. We have to adjust to change quicker and quicker.
So can I ask you to add some of your thoughts on what are some actual challenges that one can anticipate as you go from lab scale materials to scale up and manufacturing?
Right. Yeah. So one example is defects. So, right, these polymer films that we made are made in the lab. Someone in Dr. Satsing's group is very meticulously creating this film by hand. If you put any defects in there, though, the band gap is going to shrink, and that's bad. We don't want that. So the challenge is, can we scale this up to bigger industrial devices, and can they make these films without defects? So that's one example. Yeah.
Just make one mercenary comment. If you're interested in improving the polynorminine family, that's Paul Cole. He's the expert.
Data scientist here at Georgia Tech?
Yeah.
Okay.
Chemical engineer.
Okay.
And so is Greg Satsing, who's tuned in over here as well. Further questions from the students?
Oh, I think Elias has a question. I see his hand raised online.
Hi, Rishi. Congratulations.
Thank you.
Incredible PhD. So I have a question with respect to, so you've predicted some really impressive properties here. Band gap, electron injection, glass transition temperatures. Are there some harder to predict properties that you've attempted and had trouble with predicting throughout the course of your work?
Yeah, definitely. I think a good example is, so let's compare 2 things. We have TG and we have dielectric constant. So TG is an easier thing to predict because it's mainly determined by the chemistry of the repeat unit at sufficient molecular weights. At low molecular weights, it depends on molecular weight, but if you go to a high enough molecular weight, it's mainly dependent on chemistry. So that's something that's easy to predict. We just need to get one thing, the chemical structure. But dielectric constant, on the other hand, depends on other things like temperature and frequency. And so the chemical structure is not enough. For each data point, we also need to collect the temperature and frequency. And so as you add in these variables at which your target property depends upon, the problem becomes, I don't know, exponentially harder or something like that.
Anyway, I had a property that we really wanted to predict, but we were not able to.
Yeah.
And so we chose the proxy.
Yeah, thanks, Rompi. Another good example is breakdown strength. So the energy density is equal to the dielectric constant times the breakdown strength squared times some other constant. The point being that breakdown strength is super important for this application, but the mechanisms underlying breakdown in polymers are not well understood, which rules out something like simulation. And likewise, there's not a lot of experimental data out there on breakdown strength. So we can't train a machine learning model to directly predict breakdown strength. Instead, we use proxies like bandgap and electron injection barrier, for which there is abundant data. And so we can train machine learning models on that data, and we can say, okay, if a polymer has both a high bandgap and a high electron injection barrier, then based on the statistics of known polymers, we can be reasonably sure that it will also have a high breakdown strength.
Awesome. Thank you so much. Congratulations again.
Thanks, Elias.
What are the next steps to take your research and apply it to something that can be commercialized?
Yeah, that's a good question. That's more of Rompi's domain, but as an example, I mean, he has to raise the money to get all these things going, but I mentioned those 5 different levels, right? We're at 1, the basic science. So we do have another project, which is 1 step up, trying to bring these things to the next scale. So that work is ongoing as we speak.
Any application to the shipping industry?
Maybe.
Yeah, capacitors,
Oliver?
Yeah, I was just curious about something that you mentioned towards the end of your presentation. You mentioned a barrier in 2008.
Yeah.
You just say more about that and what
Yeah.
that is.
Yes, I can. I have a backup.
Dr. Lively's domain.
Yeah. Do you want to stand up here and give the answer?
No.
All right, okay. So, as I mentioned near the start of the presentation, for polymer membranes, which is the application I'm talking about, a polymer should simultaneously have a high selectivity and a high permeability, right? It should be perm selective. So there is this groundbreaking paper published by Dr. Lloyd Robeson in 1991, and he showed something interesting. He showed that for all of the polymer membranes that have been reported so far, they display this strange behavior where you can get a high selectivity or a high permeability, but not both at the same time. And you can draw this dashed line showing kind of the frontier of this performance. And this became known as the Robeson upper bound. So this was published in 1991. And since 91, since this paper, because of this paper, I think, a lot of research has gone into finding polymers that can surpass this upper bound. And so the upper bound keeps getting pushed every couple of years. And so there's a 1991 upper bound, there's a 2008 upper bound as well. And so that's the upper bound I was referring to.
Okay, thank you.
Okay, any further questions from the virtual audience? All right, if not, the general audience is thanked and excused so that the committee will continue with questions and discussion with Rishi. Thank you all for joining.
Thanks everyone online and in person. In person people, please take some donuts.
Good job.
Yeah, great
Thank
job.
you.
Great job, Rishi.
Thank you. Thanks for coming. I should turn off the.
Amazing.
recording. Yeah.
Great job.
Thanks, Tina. Love you.
See you later. Thanks for your time.